All right, so hello everyone. So this is going to be the third and final piece of Lecture 2, an extended lecture that talks about model selection and things related to that subject. And I thought I would just sort of step back and start again with the basic ideas behind AKAI's information criteria, which we're going to make considerable use of over the remainder of the semester. It was first described by AKAI in 1973 in a Japanese economics journal, did not get translated to English for some time after that. So it sort of sat in obscurity for a little bit of time. And his big achievement was essentially that he found an estimator of the expected, relative KL information. So remember, KL information is the degree to which the models differ from each other in a relative sense, relative to truth. So you have a couple of different models, and you can't measure, in any kind of absolute scale, the distance between the model and truth, but you can compare the relative distances of the two models to truth, right? And again, sometimes that's a little confusing as a concept, but let's say that you and I are standing on a road, and at the end of the road, there's some town that we're both trying to get to, and we'll call that town Truth. And I don't actually know where it is. It's somewhere down the road. I don't know exactly where it is, but I can look and see that you're standing, let's say 100 yards further down the road than I am. So I can't say how far exactly I am from truth, or I can't say how far exactly you are from truth, but I can say that you're 100 yards closer to truth than I am. And so that's the relative KL distance, or KL information, and AKAI big achievement was essentially he found a way to estimate that. And again, for historical reasons, he called it an information criteria. Everybody knows it as the AKAI information criteria. And I thought I would add a little thing here. On his 90th birthday, Google, on the Google search engine, when you pop it up on the web browser, they have little doodles of things or another, and they often are created to honor somebody that Google thinks is interesting or important on that particular day. And on his 90th birthday, they actually used AKAI. So he's not some obscure guy who only statisticians know about. This is really kind of a big deal. And in a lot of ways, it makes perfect sense that a lot of the folks at Google would know exactly who AKAI is because of his impact on model selection, and building lots of models is something that Google engineers do all the time to try to figure out who's searching for what, and so on and so forth. Now, again, this is the AKAI information criteria by itself. All right, so the AKAI information criteria, and I'm just going to refer to it, from here on as AIC, is got two components. There's a fit component. All right, so something related to the likelihood of a set of parameters given the data, -2 times the log of that, and then twice the number of parameters. And this number of parameters on the end here is essentially like a penalty thing. And remember, we talked about this trade-off between precision and bias. And so we can get, really good, reductions in bias if we simply use more and more complicated models, but there's a trade-off, and that trade-off is the variance bias trade-off. And so we could reduce the bias, but we'd increase the variance. So we want to actually have a penalty. So even though adding more and more parameters is going to make this term, very small, there's a penalty, there's a trade-off, there's a cost to doing that. And so having this term here on the end shows you that cost. So lots of parameters, this term gets small, but that term gets big, all right? And so essentially what the AIC is trying to do is essentially find a balance between the value in terms of reduction in bias by using more parameters, but balanced against the cost of increased variance in so doing. And so AKAI came up with this particular estimator for KL, relative KL distance, and he showed that the model with the lowest AIC value amongst the models that you're testing is the one that is relatively closest to the truth. Now, that's a really important statement relative to the other models, right? So if you've got 5 or 6 models, the AIC basically is guaranteeing, or is suggested to guarantee, that the model with the lowest AIC is the one that's closest to truth relative to all the other models. right? So we don't know exactly how far truth is, but we simply know that that model with the lowest AIC is the one that's relatively close to it. Now, it's always conditional on the model set, and there's an important point to remember when you think about that, and the point is, suppose you have 5 or 6 or 7 models and they're all terrible. Well, the AIC will still serve to tell you which of the models amongst your terrible models is actually the KL best, right? So one sort of graphic way of putting that, all of your models can be crap, but the AIC will help you identify which models don't smell as bad as the other models in your pile of crap. All right, so that's one way of putting it, I suppose. Now, the bonus result is that the AIC also selects the most parsimonious model. Remember, with parsimony, we're trying to get really good fit with as few parameters possible. So we want to make this term on the right as small as possible, but we want to make the fit as good as possible. And it turns out that by selecting the AIC best model, you're also selecting the most parsimonious model. All right, so that's a bonus result. It wasn't originally motivating AKAI, but it essentially sort of came out as one of the results. Now, as mentioned last time, there have been some generalizations. The AIC, like a lot of statistical theory, is initially developed on the assumptions that you got big, beautiful, perfect data, all nice and normal, everything sort of is well behaved, et cetera, et cetera. And under those circumstances, you can derive the AIC as we saw in the previous slide. However, in reality, and especially in sort of ecological reality, we're often dealing with data sets that are relatively small. And so one of the first things that emerged following AKAI's initial publication was something called the AICC, which is the small sample size correction. And the good news is that it really only has an influence on the AIC, and we'll actually look at the formula at some point, when the sample size is truly small. And once the sample size gets larger, AICC and the standard regular old AIC are basically the same number. There's some tools that we're going to look at in a moment on rescaling the AIC. This is something that we can do very easily that will help us compare amongst the models in our model set. Variance inflation factors. So again, something that we've mentioned a few times in passing is that the assumption for most of what we do is that the fates of the individual animals are completely independent, right? So each coin flip done by one animal, live or die, detected, not detected, does not influence the coin flip of any other animal, right? Well, that's not going to necessarily always be true. And so in those circumstances, we need to sort of correct for that as much as we can. And sometimes we can do a pretty good job, sometimes not so much. And there's something that we're going to do, and we'll definitely get more into this as we move along, called the variance inflation factor correction, sometimes known as the C-hat correction. And that's what is generating this Q. So Q means a quasi-likelihood. So the moment that you start trying to correct the standard likelihood structure, which assumes independent coin flips, you get into something known as quasi-likelihood. And then there's the kind of combination of these two. We can have small sample size correction and quasi-likelihood. And these show up fairly commonly in the kinds of things that we're going to do. It's nothing particularly to get overly concerned about. You just need to be aware of it. You need to have a little bit of an understanding of what these things are. And we'll definitely talk about that as we move forward. Again, with the sort of emergence of the AKAI information criteria, there have been a slew of other criteria that have been proposed. Each of them has strengths, weaknesses, so on and so forth. Just one that I'm mentioning here because it's built into program Mark is the BIC, the Bayesian information criteria. And largely what most of the criteria have, the information criteria, the IC part, share in common is some measure of the likelihood. So even if you're a Bayesian, you still deal with the likelihood. Most of the time where they differ from each other is what the penalty term looks like. So the basic assumptions underlying the penalty term. And there's a little bit of arm waving that goes on out there about, which of the two is more robust. Does one do better if the quote unquote true model is complicated or not? And complicated in the sense that it has more parameters or lots of structure. These are important things to be aware of. I don't want to discount them entirely, but by and large, for most of what you do, I would say 95 times out of 100, whether you use AIC or BIC, you'll end up largely making the same inference, at least in this kinds of data that we're going to work with program mark. Where there are differences are important, and you simply need to be occasionally aware that, well, maybe if you're using one or the other, you might be getting an inference that's determined by the source of the particular information criteria that you use more than anything else. All right, so where we left off last time was really this question. Again, we have two objectives when we're talking about estimating parameters. We want to come up with our best possible estimate at sort of one end. And we also want to learn something about biology. And it's not really a dichotomy. You do one or the other. You do both. But often the people who are working with the data tend to focus closer to one of these questions than the other. And so the neat thing is that we can use things like AIC to actually address both of these. And that's essentially what we're going to talk about for the remainder of this third part of lecture 2. Now, let's start by asking the question, well, what about the best estimate of the parameter? Well, we know that we can come up with, for a given model, the maximum likelihood estimate of the parameter, all right? But we also know that each model is going to give us a different estimate of some parameter, each different model structure. And we've looked at that briefly in the context of a couple of different things. So how do you know which model to use when your objective is to simply come up with the best estimate of the parameter? And we can do that using AIC or AKAI stuff. So we start by noting that AKAI showed that the likelihood of an approximating model. So I'm going to try as much as possible to continuously refer to models, any model that we fit to data, as an approximating model, to remind us that any model is an approximation. The model is not truth unless the model was used to generate the data in some kind of simulation context. No model is truth. They're all approximating models. And given that you're supposed to know that, maybe it's redundant to say approximating, but I actually think it's useful to say it that way because it just forces you to remember that models are just abstract structures that you fit to data. They're cartoons, they're not reality. All right, so AKAI showed that the likelihood of a model given the data can be approximated to something. Now, we've seen likelihood before, right? So if we simply zip back to where we've seen likelihood, we've looked at it in the context of the likelihood of some parameters given the data, right? So likelihood of parameters given the data. So the parameters could take different values, and we use the maximization of that likelihood to come up with the values of those parameters, which maximize the likelihood given the data. All right. So what do we got here on this slide? Well, now instead of talking about the likelihood of the parameters, we're talking about the likelihood of a model given the data. All right. So that's what you actually see down here. The likelihood of our approximating model G given the data. Right. So what do we mean by likelihood? Well, we sort of had this idea when we're maximizing likelihoods for parameters that there's some true parameter value out there, and we'd like to maximize our likelihood of getting an estimate of the true parameter. Well, approximating models are trying to approximate some unseen truth. And so we're talking about the likelihood of a given model given the data, amongst the different models. So we might have different models, and each of them has a different likelihood of being, wait for it, the one that's actually relatively closer to truth. So there's always some uncertainty. You never know for sure because all the models are cartoons, they're approximations. So what's the likelihood that a particular model, given the data, all right? So that's what we have here. And AKAI showed that it's essentially approximated by what? Well, this is the base E, so exponent base E, raised to basically -1/2 times delta I. So what's delta I? All right, so the first thing that we need to know is that delta I is the difference between the model with the lowest AIC, so we take whatever that value is, and the model that we're interested in. So we'll call the model with the lowest AIC, let's just call it 0, model 0. And let's say you're looking at model 1. And model 0 has an AIC of 100, and model 1 has an AIC of, let's say, 106.5. So the difference between those two AIC values, 106.5 minus 100, or 6.5, that's this delta value. So it's essentially delta AIC. So we simply take that value, multiply it by -1/2, and then raise it to the base E. And that will give us an approximation of the likelihood of that model given the data. Now, why does that actually work? Well, you can kind of get a little bit of a hint. I mean, there's a formal derivation of this in AKAI's paper and things that have followed. And it's not particularly the easiest or most fun read, except for a few people, I suppose. I'm not one of those, and I suspect you're not either. So let's just sort of figure this out. So what's delta AIC? So delta AIC, this delta that we see up here in the likelihood approximation, is essentially what's the AIC for the model you're interested in minus the AIC for the model that's the smallest AIC amongst the set, right? So whatever that number is, that's the smallest AIC, and here's the AIC for the model that you're looking at. And what do we do next? Well, we know what AIC is. AIC is negative 2 times the log likelihood plus 2 times the number of parameters. So for AIC sub I, there's the actual calculation for that model, model I. For AIC sub 0, the model with the smallest AIC, there's its expression. So get rid of some brackets, change a few signs around, and what do I have? Well, AKAI's approximation is this term here on the right that I'm circulating. So I'm going to do something to this expression here. I'm going to basically exponentiate it, right? And so if I do that, then the left-hand side is this term here, okay? And then the right-hand side is what? Well, it's the log of the likelihood for the model minus the number of parameters, and then minus the log of the model with the smallest AIC minus the number of parameters. And then what? Well, if I simply exponentiate things, what do I have? I have something here which should look familiar. That's my likelihood ratio, all right? So essentially, this approximation that AKAI came up with is a likelihood ratio between the model that I'm interested in, I, and the model that has the smallest AIC in the candidate model set. All right, so now that we have this way to approximate the likelihood of a given model, and again, there it is, the likelihood of a model given the data is e to the minus 1/2 times delta AIC, we can do what? Well, what we want to do is normalize that. What do we mean by normalize it? Well, we want to sort of rescale things so that we represent proportions. Proportions of what? Proportions of all the models. So we're going to generate something called a normalized model likelihood, or more generally known as an AIC or an AKAI weight, AIC weights. So the weight of a given model is given by the numerator. Well, what's the numerator? The numerator is, in fact, the likelihood of the model given the data, divided by the sum calculated over all the models. So for each model, you calculate the model likelihood, you add those up, and that's the denominator, and then each model divided into that gives you the weight, the proportion of all of the likelihoods that any individual model has. And when we actually see this, it'll make some more sense. Now, once you have these weights, then you can look at the evidence ratio or the odds of a particular model being KL best by simply doing the following. You take the weight for the best model, and if you just stared at the algebra long enough, you'll realize that the weight for the best model is going to be 1, all right? And then everything is sort of relative to that. And then you take each model underneath that, and you end up with this expression over here. So each model being each of the different other models in your candidate model set, and you end up with this expression. And what this is going to do is it's going to give you what's called an evidence ratio, or what's the probability that that model really is the one that's KL best. All right. So normalized AIC weights. These are really, really handy. A given WI, so a given weight, is considered the weight of evidence in favor of a particular model, given that one of the models in the model set must be. Right? So here's the thing. It's kind of hard to wrap your brain around initially, but with just some sort of mental imagery, you can kind of imagine. You've got 5 models, and you know that one of them has to be the closest to the truth. You're just not sure for sure which one it is. So you're using the evidence and the data to try to give you that. So what the weight is telling you is essentially what's the probability that the model that I'm looking at is actually the closest to truth. So the one with the smallest AIC is the one that we believe is closest to truth, but what's the probability that in fact it's one of the other ones? Okay, and we'll see how that works in a moment. And this is a really important concept, and this deals with the idea of what we call model selection uncertainty. We can just use AIC sort of blindly and say, well, there's a model that's got a very low AIC. That one is relatively closest to truth because AKAI said so. But he also said, no, wait a minute. There's some probability that you could be wrong. In fact, it could be one of the other models. So let's see if we can calculate that probability. And guess what? It's actually related to these normalized AIC weights. Now, it's important also to remember that they depend upon the entire model set, which sort of makes sense. All of the inference in the context of information theoretic methods is based upon the relative performance of one model compared to the other models in the candidate model set. Right? So if you add or drop a model for some reason, then you need to recompute them all the time because the denominator is going to change. Right? So looking at AIC and thinking about relative degrees of evidence in favor of a particular model is always conditional upon the other models in the model set. If you change the model set, then everything else changes too. All right, so here's an example of this. Suppose that I have 5 models that I fit to some data, and these are the delta AIC values. So what do I know about the delta AIC values? Well, based on this, model 2 is the best of the bunch, right? So that's why the delta AIC of model 2's AIC relative to itself is 0, right? And every other one of these values is essentially simply the arithmetic difference between the AIC for that model and the model with the smallest AIC. So model 1, for example, is 1.6 AIC units above the AIC for model 2. Model 3 is 7 units above, right, and so on. So pretty trivial calculation. It's simply any of the AICs minus the AIC for the model with the lowest AIC, okay? So it's like taking the minimum of the list and then subtracting every other one in the list from that minimum, or subtracting the minimum from every other one on the list. Pretty easy. Now, the problem is that what's an AIC unit? Well, it doesn't have a unit. So by converting them to AIC weights, we actually have a unit because the weights have to sum to 1. They sum to 1 over the candidate model set. So now what do we say? So now we actually have something extremely useful. Model 2 is the smallest AIC. The probability that, in fact, it really is the closest to truth, has the KL minimum distance amongst those 5 models, is 0.619. So a 62% chance that it's that model. So what does that mean? Well, that means there's a 62% chance that that model is really closest to truth, but it also means there's a 38% chance that you're wrong. All right? What does 0.278 mean? Same basic interpretation. 0.278 means that, okay, even though model 1 had a slightly larger AIC by 1.6 units, there's approximately a 28% chance that, in fact, it would be the right one. So if you, for some reason, were really, really focused on picking just one model, you might say, okay, the model with the smallest AIC, 0.62. But in so doing, you're accepting a 38% chance, at least given these 5 models, so 38% chance that in fact you're wrong and it's really one of the other ones. Okay. Now, you can also do sort of relative comparisons. Suppose that you were really focused in on model 1 and model 2. If you think about it, if you just add up those two numbers, that's a significant proportion of the total. So 0.6, 0.3 approximately. So we could say that, well, we have about twice as much support for model 2 as we do for model 1. All right. So you can use AIC weights in a variety of contexts, and a particularly important one is coming up. So AIC weights, this thing called evidence ratio, talked about a little bit earlier, and rules of thumb. All right. So these rules of thumb, I'm going to mention only because they do tend to show up, unfortunately, with some frequency in the literature, but they do have a basis in fact. All right. So again, this is the expression for evidence ratios or odds ratios. And so let's just say here's the delta AIC value. All right, so on this slide, 1.6 or 7 or 13.5. So here, just given the delta value, 2, 4, 8, 10, 15. So if you have two models that differ by 2, all right, then what? Well, that delta would go into this equation, which is equivalent to this expression. And what does that give me? That gives me the following. If they differed by 2, then I have an evidence ratio or a model likelihood of 0.37. So what does that actually mean? That means that two models that differ by 2, there's a 37% chance that the model with the bigger AIC is actually the KL closest model. Or in other words, there's a 63% chance that if you simply focused in on the model with the smallest AIC, then that you would be wrong. And that in fact, that the one that was only 2 away is maybe the one that's closest to truth. Now, what if the delta AIC was 4? Well, now the model likelihood drops to 0.13, right? And when it's 8, 0.0183, right? And so what these evidence ratios are is the odds of being wrong. So you got 2.7 to 1 chances of being wrong, 7.4 to 1 chances of being wrong, 54.6 chances of being wrong. And what you see clearly then is AICs, the delta AIC rather gets bigger and bigger, then the chances of you making a mistake and that model with the larger AIC actually really being truth gets very small. So this basic observation, which is simply a matter of plugging different numbers into the equation at the top here, is what led to a set of rules of thumb. So when the delta AIC is less than 2, so sort of like this or smaller, then you're reasonably safe in saying that both the models are equivalent in terms of the relative distance to truth. So if you had two models and they differed by like 1.1 in AIC units, you're relatively safe in saying that you really can't tell the difference between the two models. They're both, likely to be equally good at approximating some truth. When you're sort of between 2 and 7, so, in this range up here, you have some support for a difference between the models, okay? It's not perfect support, but you have some support. So if you had an AIC difference of 4, there's a 14% chance that you're right, but that means that there's a 86% chance that you're wrong. And so, you have some support, but not full support. When your AIC is bigger than about 7, delta AIC is bigger than 7, you got strong support. You can pretty well say, no, there's a difference. And the model with the lowest AIC of the two that you might be comparing absolutely is likely to be, the one that's closest to truth. So these rules of thumb show up. They're convenient, which is why they tend to persist in the literature, but they're really not what we should do. We should try to be explicit when we actually calculate probabilities of things as much as we can. All right, so let's just jump out to the computer for a second, and I want to show you the calculations of these things. So, I'm going to hop out here, and I'm going to go into my script for looking at the survival of deer as a function of whether or not they are males or females. So we have two competing models. It's not, really much of a model set per se, but we do have two different models. So let me kind of change the dimensions of these a little bit so we can see. So we start off by loading our optimization toolbox, as we've done before. We set up our function for the model that does not have a sex difference between the two. We go ahead and run that. All the results are in results underscore no sex. Run that. And now I build a competing model with sex in it, do the exact same thing. All right, do the optimization and run that. And now what? Well, now I'm going to do everything that we have talked about. So in the previous lecture, we looked at the likelihood ratio test. So here's the likelihood ratio test. We run that. And what did we have? Well, there's the likelihood of the model without sex. Here's the model with sex. We know that the model that's got sex in it has more parameters. It's a bendier ruler, so it's going to have a likelihood that's closer to 0 of the two. There's the difference, forms the basis for our 1 degree freedom likelihood ratio test. And there's the probability, so 0.0023, that we would observe a difference as large as that by random chance alone. So we would say in so many words that there's a difference between the models and that the model, even though there's a a change in the likelihood with the penalty and all that, or not with the penalty, but change in the likelihood that there's evidence of a sex effect. And this is essentially what we talked about in the previous lecture. All right. So now let's do the AIC. So remember, AIC is just negative 2 times the log likelihood plus 2 times the number of parameters. Well, there's your negative 2 times the log likelihood. So we simply add to it 2 times the number of parameters. And so when we do that, and you should, confirm this for yourself when you either run the script, you can even do it by hand. There's the AIC model with no sex. There's the model with sex. And if you look up here, it makes sense, right? So 137 is the model without sex, right? So it's got 1 parameter. So that number plus 2 times 1, or that number times 2 rather, is simply that number, all right? 128.3876. This is the model with sex. So the number of parameters is 2. So 2 times the number of parameters would be a penalty term of 4. So 128.3876 plus 4 is that number. And then the delta AIC is just one minus the other. All right. So the model with the lowest AIC is the model with sex. The next model is 139. So 139 minus 132 is 7.24. So that's the delta AIC. But we want to normalize that. So the remainder of the script that you have does just that. And if you stare at it for a few minutes, you'll actually see how it works, hopefully. But what do we have? So there's my delta AIC, and there's my AIC weight for the model with sex, and there's my AIC weight for the model without sex. All right, so jump back into PowerPoint here, and here are the results from the R script, sort of cleaned up and a little bit easier to see what's going on. There's the AIC expression at the top of the screen. All right, so AIC is simply the fit, the negative 2 log likelihood plus 2 times the number of parameters. We're not going to fuss around with quasi-likelihood or AICC, the small sample correction at this point. Here's the no sex model, the log likelihood negative 68.81. Here's the with the sex model, it's bendier, so we have a smaller, closer to 0, negative log likelihood. We take minus 2 times that, add the 2 times the number of parameters, and we get our AICs, 139.6 and 132.4 respectively. Now, using the classic likelihood ratio test, we had a chi-square statistic with a 1 degree of freedom of 9.24. That's strongly significant at an alpha level of 0.05. So we would conclude, using sort of standard classical inference thinking, that we have strong evidence for a sex effect. Okay, so that difference in the likelihood is significant in a statistical sense. And then we would like to hope that also means in the biological sense. Now, what do we get when we do the AIC approach? Well, here we have a table. So we have our 2 models without sex and with sex, so no sex with sex. The model with sex has the smallest AIC, so 132. So the delta AIC of that model with respect to itself is 0. And the delta AIC for the model with no sex, which has a bigger AIC, is simply 139.6 minus 132.4, which gives me a number of 7.24. We calculate the AIC weights based on just these 2 models, and these are the values that we see here. So there's a 97% chance that, in fact, the model with sex is the one that's KL closest to truth, relatively close to truth compared to the other model. So 97%, meaning there's a 3% chance that you're wrong. And so the conclusion then is you would say, with some authority, that the model with sex has much more support than the model with no sex effect. Again, if we talk about it in terms of weights of evidence, we can do the same thing. The model likelihood is 0.027, this is what we have. Or we can say there's a 37-to-1 chance that, in fact, we're wrong, which is essentially saying the same thing. Okay. Now, while AIC weights and model likelihoods and rules of thumb and all those things we've seen in the previous slides are convenient, they don't quantify the degree of uncertainty in our model selection over all the models. So we need to do a little bit more than that. And that leads us to the extremely important topic of model averaging. All right, so AIC tells us, when we create these normalized AIC weights, the relative probability that any of the models is closest to truth, relatively closest to truth. And suppose you have a model that's 65% AIC weight. So it's 65% probability that that model amongst the candidate models is the one that's closest to truth. So there's a 35% chance that you're wrong. So do you want to base your estimate of a parameter on that one model when there's a 35% chance that you're wrong? And the answer is maybe reasonably no. So what do you do instead? No problem. You're going to make a weighted average of the parameter over the different models in your model set. And what are you going to weight the average by? The AIC weights. And that's all this is. And you're going to see exactly how that works in a moment. Now, not only do we have an average, but we need to have an estimate of the variance of that average. And that's what the second expression is here. And it's important. It looks a little complicated, but it's actually, very important that you step through it. So let's do that. So the overall variance of this weighted average is a function of basically three things. The weight associated with the model, that kind of makes sense. Models that have a higher probability of being closest to truth have higher weights. They contribute more to the average. Okay, so that's this piece. But what about this stuff in here? Well, let's just look at it carefully. The stuff on the right is the square of the difference between the estimate of the parameter from any individual model and that average. Okay, so this is a measure of the variance that's due to differences among the models. And this is the variance of the parameter given the model. So we actually have two sorts of variance that we have to take into account. One, every time you estimate a parameter with a model, there's variance in the estimate. So there's model-specific variance that we have to account for. And over here, this is the model selection or model selection uncertainty. This is dealing with the fact that there's uncertainty amongst the models. So each model's estimate, which you're looking at here, differs from the overall mean. So we have both of those. Okay, so this is the variance that we're actually interested in, because this variance takes into account the variance within a model and among the models. So here's a quick and dirty example of how this works. These are 6 different models here indicated. Don't worry about the notation. This will become something you're very familiar with in due course. And here's the estimates of some parameter. All right. So this model here says it's 0.91. This model, the next one, says it's 0.71. So that's a huge difference. So how do you know which model you want to look at? Well, they're the variances of the estimates. So for each of the models, there's the variance of their estimate. But these are the AIC weights that we've just been talking about. So here's the AIC weight for each of the different models. So 0.86, there's an 86% chance that this model amongst those 6 models is the one that's really closest to truth. All right. So that means there's a 14% chance that you're wrong. And largely, there's a 14% chance that it's the next model. All right. So 86% chance that 0.91 is a good estimate of the parameter, 14% chance that in fact, no, it should actually be 0.71. And rather than worry about that chance that you're wrong, you simply weight the average. Okay, so how do you do that? You simply take each of these estimates and weight them by the AIC weight, and you come up with a weighted average, and that's it. It's 0.88. All right, so it's close to 0.90, but it's not exactly 0.90 or 91. It's a little bit below, reflecting the fact that it's lower than that for some of the models that do have some weight. And what's the variance? Well, you take each model, its AIC weight, there it is, and then you're going to multiply it by the sum of two things, the variance of the parameter estimate, and then each of these estimates minus the mean that you've calculated squared. And if you sort of jump through this, you're going to see that that's exactly what we're doing. So 0.8565, which is the weight for the first model, times the sum of the variance of that parameter estimate for the first model, plus the difference in the parameter estimate minus the mean squared. Now, if you just look at a couple of these, you'll see it would not be a difficult calculation if you actually had to do it by hand, but the good news is you never will. All right. So coming up with our best estimate of parameter, the best estimate we're going to see is our model averaged one. All right. It deals with the fact that we have uncertainty in our models. Well, what about learning something about the biology as another possible agenda? Well, one tool that isn't a perfect tool, but it works really well under certain circumstances that we'll talk about, is to make use of what are known as cumulative AIC weights. And cumulative AIC weights is one way that you can inform on the relative importance of a particular factor that you include in your model. So here's a really kind of artificial, trivial example, but it'll get the point across. Suppose you're doing some kind of modeling and you're interested in 3 different variables that you think influence something that you're interested in. All right. So, and we'll just call those X1, X2, and X3. So Y, some variable Y that you're measuring, is a function of X1, X2, and X3. So maybe Y is body mass, and X1 is how tall you are, X2 is percentage of fat, and X3 is whether you're male or female, what have you. It doesn't really matter, but you get the basic idea. So you fit each of these models, and here we have 1, 2, 3, 4, 5, 6, 7, 8 models to the data. Now, what do you notice? Well, one of the models doesn't have any of those 3 factors. One of them has only one of them, or actually 3 of them only contain one. All right. 2 of them contain, or 3 of them contain 2 of the factors, and only one model contains all 3. All right. And so for each of those, you calculate the AIC weight, and there they are. So we see right away that the model that has variable X1 in it and X3 has the highest AIC weight. There's a 50% chance that that model is KL closest to truth, but there's a 50% chance you're wrong. But our focus here with these cumulative AIC weights or importance weights is to say, okay, we have a model that has factor X1 and X3 in it. It's the AIC best model, but what about all these other models? What's the evidence over all of the different models? And it's actually relatively easy to do. You simply say, okay, for variable X1, what's the AIC weight for every single model that contains that variable, and just add them up. So for X1, you would be adding 0.1, 0.04, 0.5, and 0.15. And if you add those up, you get 0.79. And you do that for each of the different variables. And these are the cumulative weights for each of the variables. 0.79 for variable X1, 0.35 for variable X2, and 0.85 for variable X3. And so what do we conclude? Well, that variable X1 and X3 are probably about twice as important to the overall variation that you're looking at as is variable X2, and they're roughly equal to each other in their importance. And we can do a little bit more than that, but that's essentially what we use this for. All right, so here's our big summary points. We're going to do multi-model inference moving forward. We're going to model average. We're going to think about the importance of factors. We're not going to talk about a single model being better than another model by any criteria, either p-values in a likelihood ratio test or AIC, but we're going to talk about what can we learn by looking at all of the models. We're going to model average because it corrects for the uncertainty in model specification, which is unavoidable if all you have is a single model inference. All right, so anything that bases what they're doing on a single model is ignoring model selection uncertainty. We're going to look at model weights and averaging. Now, for Bayesian folks, people who do Bayesian statistics, that can be kind of tricky, but it's doable. We're going to focus primarily in this course on non-Bayesian, or what are known as frequentist approaches, but that's essentially what we're going to do. Okay, so lecture 1 and lecture 2 cover a lot of the conceptual background that we need to start to analyze the data using program Mark. And that's what we're going to start with the next lecture. It's an introduction to Mark, and you're going to see fairly quickly how the stuff that we've covered in the first 2 lectures feeds directly into the way that Mark works. Now, I would be remiss if I didn't point out a couple of things. The advent of AIC in the literature for ecologists didn't emerge really until the year 1998, when Ken Burnham and David Anderson at Colorado State University looked at what AKAI had done and figured out that this is exactly the kind of thing that we need to do in ecology when we're dealing with circumstances where we don't do experiments. Right? So the first edition, 1998, and the follow-up edition in 2002. Now, prior to 1998, I don't think any of us could think of an ecology paper that ever thought about multi-model inference or AIC or any other information criteria. So the fact that probably half the papers that you see now use it or appeal to the idea is entirely due to Burnham and Anderson writing their books, so the first and the second edition. Now, having read these books, both editions, some parts of it are very technical, and that's entirely Ken Burnham's fault. Right? Because he's the mathematical statistician and he writes for other mathematical statisticians. And there are a lot of mathematical statisticians that are also normal people, at least by my standards of that. So David Anderson, his lifelong colleague, the late David Anderson, he passed away not too long ago. He said, I'm going to write a gentle primer for this. So I'm going to take a lot of the underlying real dense math theory out of it. I'm just going to collapse it all down into how do you actually do this in application. So I would say if you're a graduate student, you need basically both of these books. If you're an undergrad student or you don't want to get really too technical, Anderson's book, it's short, it's inexpensive, paperback. Neither of them are particularly expensive, but if you had to pick one and you were willing to just assume that the smart people got it right without really staring at the equations, then Anderson's primer model-based inference for the life sciences is really good. Both of them are excellent. It's just that there are some technical chapters in the original textbook that are fairly daunting. You could skip them, I suppose, but they're not an easy read. This picture, this is Ken Burnham to the left. This is an unusual picture because that's the only time I think in my life I've ever seen Ken Burnham in a suit of any kind. And I'm not one to talk. I never wear that kind of stuff. But Ken is even more extreme in that direction than I am. So he's wearing a suit because standing to Ken's left is AKAI. And this was the event of the very first Kyoto Prize, which many of you may know is awarded now annually to people who've contributed the most to our understanding of climate science. And so it's very kind of interesting to wonder, well, why did they give the first one to AKAI? Well, they gave the first one to AKAI because the awards committee, and it wasn't because it's a Japanese award given to a Japanese researcher, it was because they understood that without somebody like AKAI coming along, we're going to have all these models about climate change, and we're not going to be able to do anything to really sort of figure out how do you make inference over all those models. We're not doing experiments. We're watching stuff and telling stories. So AKAI provided at least one of the very important tools that now we consider when we're thinking about selecting amongst models. In the context of climate models was essentially what the Kyoto Prize was focused in on. So extremely insightful on the part of the committee, and equally insightful, they invited Ken Burnham to come over and give the sort of nominating awards speech. And Ken was there to say, hey, AKAI did this thing, and oh, by the way, it's really important. And so the committee not only understood AKAI to be sort of vitally important in a lot of the way that we think about things, but they were also very aware that this ecologist who sits in Fort Collins, Colorado, figured this out before a lot of us did and wrote about it with his colleague, David Anderson. And so they said, boy, that's appropriate. Let's get the guy who made AKAI available to the world, Ken Burnham being one of them, and come and have him give the big speech. All right, that's it. So next lecture, we start with Program Mark. Take care, everyone.